Thank you to the organizers for inviting me here. This is a great meeting. I have to say my talk is a little off topic, and I was worried about that, so I promised to say conformal 4 times, and that includes this time. So, all right, so I start my talks in this topic the same way. I start with the Schwarzschild KdV equation, which is that equation there. Is ux times s of u, and s of u is the Schwarzschild derivative of u. I consider that equation to be u to be a map from R2 to RP1. So it's really homogeneous coordinates that I'm looking at. And that equation is invariant under the projective group. So I can write it in terms of the invariant, which is the Schwarzschild. And if I write it in terms of the Schwarzschild, which is the invariant under the projective group, invariant under the group, I mean the group takes solutions to solutions. And because invariant, I write it in terms of the Schwarzschild, and I get the KdV equation, hence the name. And the KdV equation is a very well-known integrable equation, and we'll talk about that a little bit more later. So we say that the Schwarzschild KdV flow is a projective realization of this KdV equation, because you are viewing it as a flow of, well, if you want curves in RP1, really reparametrization of RP1. You can also say that the KdV equation is the invariantization of the Schwarzschild KdV. All right. So
we have this top evolution equation.
Yes.
And it would flow u according to that, and s of u flows according to.
Yes.
Sorry.
That's exactly it. Okay.
So is the top one integrable?
In the sense that this one is.
Oh, okay. Okay, so modulo SL2, okay.
Right. Okay, so here is another example. You have this equation, which is called the vortex filament flow, and U now is a flow of curves in R3, and it flows as the curvature times the binormal. So this is standard curvature times the binormal. If you write this in terms of the invariance now, this flow is invariant under the Euclidean group. So you can write it in terms of the curvature and the torsion. And if you use what is called the Hashimoto transformation, which is this thing here, then the solution, the equation that these invariants are going to be following is the nonlinear Schrodinger equation, which is another completely integrable equation. Now, this, if you write this out into real and imaginary part, these two, kappa 1 and kappa 2, are actually what is called the natural curvatures. And they are obtained by, instead of choosing the normal, binormal, and tangent, use the tangent, and then you use 2 complementary vectors that differentiate in the direction of the tangent. And those are called the natural frame. And these are the natural curvatures. Back. So these are the natural curvatures, and they are solutions of this nonlinear Schrodinger equation. What is this? It's just some open subset of R2. This is all local, so I'm not saying this exists for all time.
Can you just come back for this Schwarzschild KdV?
Yeah.
So the logic is you solve this Schwarzschild KdV using the methods you use to solve KdV.
Yes.
And then
you lift it up.
The function u
yes.
From the Schwarzschild.
Yes. And then you look at the flow. Yes. So let me talk a little bit about that.
So you take, say, one solid solution for the Schwarzschild.
Yes. So we have a paper in which we do that. We find solitons for the KdV equation, and then we integrate it to the vortex filament flow, and then we actually graph it to see how it looks. So now that we get there, which is actually where I was going. So let's go there. These equations are soliton equations. So they have these special solutions that are solitary waves. KdV is used to model flow, actually waves, in channels that are not very deep and they are narrow. So in fact, So Madison has, in downtown, has this water fountain, which is really narrow and not deep. And then I put my kids one on each side, and I thought to make a solidon, and they already know how to do that. You put your hand in, you push the water, and then you see a solitary wave, and waves always going in groups, right? I mean, if you go on the beach, you see all the waves coming, but this is just one bump going, and then the other one produces another one, and then you see them crossing, and they don't change the shape. That's part of their properties. They don't change, they only change the face, but they cross each other and remains there. So they are extremely, the solutions, the soliton solutions of these equations are extremely stable. They keep their shape forever, and they have a very strong shape that they won't change. Okay. Not quite. Okay, so what I want to show you is how does one of those lifts for this one look? Okay, so I'm going to take a simplest soliton for the Schrodinger equation, and I'm going to lift it to that evolution, which is ut equals kb. Okay, and here is the first movie. I have to click here if I remember. So this is Mount Etna, the volcano, and it's just producing for you that soliton up there. And you can see how it moves following the other equation. It's moving in the direction of the binormal. It's actually not going very fast, and it goes slower and slower as it grows because it's proportional to the curvature. And as it gets big, it goes slower. And you can see how the shape remains forever, even though there is wind and atmospheric conditions there, still the shape stays on and on and on. And it goes, in fact, this video goes on for a long time, and it's cut a little bit short. All right. Now, so these geometric realizations have similar properties to the solitons they are realizing, right? They are very stable. They remain for a long period. Now, I'm going to ask you to do an exercise. I'm going to show you what happens when you take two of these realizations of solitons, and they collide frontally. Okay? So waves, they cross, and they don't do anything. But what happens when I take these two guys and I collide them frontally? Okay, use your imagination, get wild, and come up with something. Just think, it's going to happen.
You take two small rings, you mean?
Two small rings, and they collide frontally. Okay, two small rings collide frontally. What's going to happen? See if you can guess it. So the structure is so strong that even though they can't cross, they can't do anything, they expand until they can, and then they split into little solid, into little not solitons, it's actually vortices. All right, so the bad news is that the movies are over. I have another one, but it's too long, and I'll keep it for the end. If we have time, I'll show you the other movie. It's really cool. And now I have to show you math, unfortunately. Okay, so here is some other completely integrable system that have realizations in all sorts of geometric manifolds. Sine-Gordon modified KdV, three-dimensional, Boussinesque in RP2. Gelfand-Dickey flows or generalized KdV systems in RPN. Sawada-Kotera as a flow in equifying geometry, in projective flows. There are lots of this, tons of this. Decoupled KdV equations can be realized in conformal flow in the sphere Sn, flow in two Grassmannians, flow actually in n Grassmannian in R2n, flows of pure spinors, flows of Lagrangian planes, lots of these guys. I'm going to focus actually in these decoupled systems of KdV. How do they show up in these parabolic manifolds? And this is another one. Okay, so this is a list of people that work in this area. Or has worked for the last 10, 15 years. I have to say the movies I borrowed from Uri Pinkel, who uses this stuff to model smoke. And you should go to his website. He has incredible movies. And he let me borrow some of them. OK, so what do these completely integrable systems have in common? The list that I put before. So they live in flat homogeneous spaces that look like that. Most of them, and that's just by choice, I was just choosing the parabolic ones. So they live in parabolic manifolds with a 1 gradation. And this is our example, the Moebius sphere, the Lagrangian Grassmannian, pure spinors, etc. These are the different choices of group. These are all flat. Most of them are KdV type by choice because I put the KdV type there. And they are also bi-Hamiltonian systems. So they have 2 Hamiltonian structures with 2 different Hamiltonians, and these structures are compatible. And in fact, having these structures is what allows us to integrate them by generating a whole list, an infinite family of preserved quantities that generates it in the sense of what is called Liouville integration. So these are important for me, in particular, when I talk about these equations. All right. Ooh, yes. So these Hamiltonian structures are actually linked to this background geometry where I'm realizing them. And I want to show you how this comes about. Because the background geometry is going to, this geometry where I'm realizing this, these equations actually generate the structures and give some of the properties and guarantees that there is such a geometric realization. And I want to, so this is the example I'm going to be using. It's a little complicated, maybe to follow, maybe not, but it's, it shows a lot of the problems that you find when you do this stuff. So this is the case of G is all 2n to n, so it's pure spinors in 2n dimensions. And this is going to appear in the Annales de l'Institut de Fourier, or however you pronounce that. I don't know French. So here is the Lie algebra, and I'm going to represent this Lie algebra degradation this way. So this part is the G1 part, this is the G minus 1 part, and this is the G0 part. And here, Z, Y, and A are skew symmetric, and B is symmetric. And A and B are actually considered the symmetric, skew symmetric part of a metric C that represents the 0 portion of the algebra. So this is one way to represent this algebra, this gradation. And I can factor locally the group accordingly. So I'm going to factor an element in the group into an element in G1 corresponding to the algebra, and G minus 1 and G0. And they can be written this way. And if I do that, then Z and Y would be skew symmetric. Theta is just any matrix. And the parabolic subgroup is going to be the G1, G0 portion. So if I quotient by that, I'm going to actually have this part here only. So I'm going to be able to represent locally the spinors as skew symmetric matrices. That's what we get from this representation. OK, so this is the manifold pure spinors. And this is what I just said. I can just take a section of this quotient to be represented by these matrices, where U is skew symmetric. OK, so I can also find the action of G on M using just the standard definition. And this is, with this factorization, it looks like this, which is a very nice formula because it really looks like a projective type of action. OK, so let's go back to general case, not the spinor case, just the general case. So I have to talk about, because of how I approach this problem, I had to explain to you what a group moving frame is. And this is, at first, when you see this definition, you think it's really weird, but it's something you all know and knew for a long time. So the definition of a group-based moving frame is due to Fels and Olver, but it appears already in the work of Cartan and Green and Griffith. The definition says is a map from the jet space of the manifold to the group that is equivariant respect to the prolonged action of the group on the jet space and the right or left action of G on itself, which sounds really weird and bizarre, but what it's telling you is this. So there is a way of describe the curvature of an Euclidean, let me put this in here, the curvature of an Euclidean curve on the plane that is very well known. Say that you have a curve here, and you want to define the curvature at that point, right? So what do? You translate that point here, right? And then you rotate it so that it's tangent to the, so you rotate it. I don't know if I can rotate this, but okay, down like that. And then so this is tangent and unit there, okay? So you're making this point 0, 0, and then this point 0, 1. And then you look at the second order term and you say that's the curvature. So most people know this way of calculating a curvature. So what is the moving frame here is the element of the group that is taking that curve here. So this curve is taken here by a translation and a rotation, and that element in the group gives you a map from the jet space because it's defined by the curve. It depends on the curve and the derivative. So it gives you a map from the jet space to the group, and that's the moving frame. So the moving frame is just a way of looking at this group action. So I guess the key thing is that that group actually carries information about the curve, and enough to know everything about it. And I left my click here. All right, so that's the moving frame. And Fels and Olver actually wrote a theorem just saying exactly what I just told you. If you assume that you have these normalization equations, you take u and derivatives to constants. If you can determine g by doing that, then g is a right or left moving, is a right moving frame actually, and the inverse would be a left moving frame. Okay, so that's the group action. All right, more definitions. If you have a left or right moving frame, if it's a left moving frame, then you can define this to be the Moret-Cartan matrix. If I have a subalgebra GLN, then this equation here, rho x equals rho k, we call it the Serre-Frenet equation, just because that's how moving frame, the equations that are moving frame satisfied are called usually the Serre-Frenet equation, so we call it like that too. And then this operator minus ddx plus k, I call it the Serre-Frenet differential operator, just to go with it. All right. So there is a theorem by Hoover that says that the entries of this k, of these Moret-Cartan forms, actually generate any other differential invariant of the curve. So any differential invariant of the curve you started with will be a function of these entries of k and their derivatives. So it really is going to tell you everything about the curve, that element in the group that is transforming the curve. Okay? All right, so let's go back to the spinor case and then see what a Serre-Frenet equation looks there. Maybe. No? Yes. Okay, so I'm going to choose these normalizations. I'm going to take u to 0, then ux, I'm going to take it to the symplectic matrix. These are skew-symmetric matrices, remember? So I take it to the symplectic matrix. I'm taking uxx to 0. Now, uxxx, the third derivative cannot be normalized completely because I have third order differential invariants, and they are going to show up there. That's that d, and we go back to that d in a minute, but those would be there. And then I have to take 3m normalizations in the fourth order, and I'm not going to go into details of how to choose those. It's a little technical. So I just choose some in there. And then I just find G, and that's a right moving frame, and I write the Moret-Cartan matrix, and it looks like this. The -1 element is the symplectic metric. The +1 element is 1/8 of that D, the third order ones. And here I get another matrix. So D has, I forgot to say that it's block diagonal, but I'll talk about D in a minute, with the third order. And in case 0 is a symplectic matrix, and it's sort of actually carry a lot more importance than I thought at the beginning. The diagonals of R1, these are all, so it's symplectic, that means that R2 and R3 are symmetric, and then R1 has a diagonal. the diagonals of the three have the highest order invariance. So it has the generators of fifth order and higher. There are no higher ones, by the way, in dimensions bigger than 3, but, or n equals 3. Anyway, so it's fifth order, and then outside there, those diagonals, you have the fourth order ones, and then you have the normalizations, the 3n normalizations that I chose there, normalized 3n entries. And so again, diagonals is the highest order. Outside there is 3n normalized entries, numbers, and then fourth order. Okay? Now let me tell you about D. So differential invariant is said to be of Schwarzian type if when I change the variable in the invariant, it behaves like the Schwarzian derivative. That means it's going to be itself and then a multiple of the Schwarzian of the changed variable. So the Schwarzian derivative behaves like that with s is equal minus 1. So if it has this property, I say it's the Schwarzian type. Okay, so let's go back to the spinor case and look at the third order ones. Come on. So the first normalization equation for the spinor was this equals the symplectic matrix. Okay, so I can choose always a matrix. So this is a generic case, right? So generically, I can choose a matrix so that this is carried to G, and I can choose that up to an element of the symplectic group, right? So such a choice, I'm going to call it the inverse square root of Ux. And of course, it's not well defined because it's only defined up to an element of SPN. Okay, so I just take any choice of that, and then I call it the square root, the inverse square root of the derivative. The second normalization looks like that, and then the third one, which is where V, so this solved for Z, which is good. That was another part. This is the +1 portion of the moving frame. And the third normalization equation, you can write it like this. And here you can see how that looks.
Can you just clarify, so where are these curves? These are maps from walls to walls?
What it?
You're talking about curves, right?
Curves.
Right? So
He wants to know what these maps are. So they are curves in two variables, and they go into G over P. So it's a spinor curve. So skew-symmetric matrices in local.
So this is a one-parameter family of
Yes.
curves.
Yes.
And these curves are curves in where?
In G over P.
In
In spinors.
Right. And there is this projective geometry, right?
No. This is spinor geometry.
Spinor geometry.
Yeah. So I have O to N to N
But
acting.
the is there because
Oh, I'll tell you in a minute. Wait to the end, and I'll tell you how the projective geometry shows up. Okay, so I'm going to call this. So let me go back. That whatever square root I want to put in there, actually geometrically there are some that are better than others, but for this it doesn't matter. I just pick one, I put it there, and then I still have this symplectic group that I can add, that I can use. And what I do.
The U is taking values where?
In coordinates, the U are taking values in skew-symmetric matrices.
The U is a skew.
Because I'm representing the spinors that way.
Okay, so the 1 plus U, 1 minus U, then you have these.
Right, so it would be this matrix of 1 plus U, exactly. Any more questions?
So for example, I mean, it could be in the Lie algebra of SO3, or is that too trivial?
We're supposed to be doing a split figure. It's the SO3 theory. And then it's isotropic, and then she's graphing over the Lie algebra, Brian graph over tangent space.
So what's the kind of not visual? What was the simplest situation? Lowest dimension, simplest equation.
Just take any skew-symmetric matrix. You know, make a change with T and X.
Right.
That would be locally what it is. This is not, this is, no. This is just, I mean, I'm really taking just the group divided by the parabolic group, and I'm just taking a curve there. That's it. Okay? Nothing else. All right. Okay. So let's go back again. I take that element here, and I still have this symplectic action on it. So I'm going to use it to diagonalize it. So there is a theorem that says that any skew-symmetric matrix can be diagonalized by an element of the symplectic group. So I just choose that one by that action, actually, exactly, of the symplectic group. So you just take the symplectic group, you diagonalize it, and that D is a diagonal that has the eigenvalues, the complex part, of course, because there is no real part in there. Okay? Okay, and then I call this the Spinor-Schwarzschild derivative, just because it looks like it. Okay? And it's not well defined, it's well defined up to the action of the symplectic group. So in fact, the generators of the third order invariance are the eigenvalues of this Schwarzschild. So that means any third order invariant for these curves will be a function of the eigenvalues of the Schwarzschild derivative. All right?
There's some ordering problem in this derivative.
Yes.
You make it a choice here.
Yeah.
A choice, or it's better than other choices.
I don't think so, not for what I do, but I don't know if for something else would be. I don't know. All right. So the very clearly, the Spinor-Schwarzschild derivatives is of Schwarzschild type. You can just check that directly, and the eigenvalues will be 2. So these are the Schwarzschild type invariants for spinors. Okay? I have to say that there is a similar one for Lagrangian Grassmannian that was originally defined by Valentin Ovsienko. He actually imposes an extra condition on this because he needs it for what he calls the projective geometry of Lagrangian Grassmannian. So this would be like the skew-symmetric version of the symmetric version for the Lagrangian. Okay. So now I want to show you the evolutions of KdV type are actually linked to invariance of Schwarzschild type. And to show you that, I have to go back to the general case and to the Hamiltonian structures. So I'm going to go back a little bit and then see how the Hamiltonian structures for these integral systems are generated. So assume I have a flat manifold and G is semi-simple. Then there is, I'm going to assume that the curves have a monodromy because I want the invariance to be periodic. So I'm going to assume there is a monodromy here in those curves. And then it's this theorem that says, and this is general for any homogeneous space, so it doesn't matter that I'm in a spinor or not. So there is a theorem that says that there exists an open set inside the loops in the dual of the algebra, such that if I make the loops in H act on that using the gauge transformation, then the quotient can be identified with the manifold Moret-Cartan matrix associated to a normalization. And let me make a picture of what I mean here. Well, I'll do it here. So on the one hand, I have the group acting on the jet space, right? And then how do I find a moving frame? So I have these leaves here. And how do I find a moving frame? I choose normalization equations, which really is just a transfer section to those leaves of the group. And in fact, it doesn't have to be constant. It could be something else as far as I have a transfer section. And then I say the element of the group that takes whatever jet there, that's going to be my moving frame. That's really what the moving frame is. So what I'm saying in that theorem is that once I fix this, and now I have a completely different picture. I have loops in the dual. And in here, I have the action. So I didn't put it there. The gauge action. I have the gauge action of H, of the isotropic subgroup. And I have these leaves. And what I'm saying is that once I fix a section there, I'm actually fixing another one here. And this section can be identified with a set of the Mori-Cartan form matrices that correspond to this one. So there is this connection between these two pictures, and is given by the Mori-Cartan or by the Serre-Frenet operator. So this can be identified with an element of the dual. And once I do that, cutting here is the same as cutting here. And maybe this is not so obvious, and I don't know if I can spend a lot of time explaining this, but if you want to know, it would take probably about 10, 15 minutes to see why this is true. And it's actually not a big deal. OK, so once I have this in here, how do we generate these Hamiltonian structures? Well, if G is semi-simple, now I look at loops in the dual of the algebra, and there are two well-known Hamiltonian structures here. You consider two functionals on the loops, and then the variational derivatives are just an element in the algebra, loops in the algebra. And then if I identify G with this dual, what happens is that I can form this bracket, and these are well-known brackets among people that do integral systems. And then there is another one here. This is really a family because it's for any constant element in the dual. And I'm identifying G with G star. I need that. They're semi-simple, and I can do that. So these two are compatible. They're Poisson structures. Yeah, they're Poisson structures or Hamiltonian structures. They're the same thing. And they're compatible. So if I add them, they're still Poisson. And this is always a good news, because then you can use them to integrate whoever is by Hamiltonian, right? So the question now is, well, now I have this quotient in the dual of the algebra, in the loops, and I have those brackets. Can I reduce it here? Right? I just have a quotient. So the theorem is that the first Poisson bracket, there are two, right? So the first Poisson bracket I can always reduce. Reduces always to that quotient, just by usual Poisson reduction. And so it gives me a Hamiltonian structure on the representation, on the section of this quotient, and that's just my invariance. So I have a Poisson structure in that invariant space. And I can, if K can be represented as an affine subspace, any reduced Hamiltonian is going to have guaranteed a geometric realization in the manifold. Okay, so now it's not on the invariant space, it's on the manifold. Now, this is a little tricky to explain how these geometric realizations come about. So I'm going to skip it. But again, if you want to know, I'll be happy to tell you. So what this says is that this quotient, I can take my first bracket, reduce it here, and if I have a Hamiltonian system there, I have a guaranteed geometric realization on the manifold I started with. This is true for any homogeneous space. This is not true just for spinors. And the second bracket doesn't reduce always. It reduces sometimes, so you have to check. Okay, every time you check, does it reduce or not? But if it does reduce, then I have a bi-Hamiltonian pair, because the original ones are. So then I have two bi-Hamiltonian pair. All right. So I'm going to call the reduction first the geometric Poisson bracket, just to know which one it is. So let's go back to the spinor case. Now, this reduction business works for any homogeneous space. So I go back to the spinor case, and I get one reduction. So I have my Hamiltonian structure, and whoever is Hamiltonian with respect to that has a geometric realization, and I'm good. Okay? So the interesting question is, can I reduce the other one? Can I take the other one and reduce it? Because when that happens, usually I do have an integrable system associated. Then I have a realization for the integrable system. So you do that, and it's not. So you say, oh, that's too bad. So you don't have it. You say, so what? I don't care. So what am I going to do? I'm going to look at that submanifold of this and wonder, is there a submanifold here, inside there, where I can reduce it? Maybe I can't reduce it to the whole thing. But is there a manifold here that would be a Poisson submanifold, so I still have that, and I can reduce the other one to that. Okay? And if that happens, well, maybe I can see which curves correspond to that submanifold, which curves have those invariants. Okay? So instead of looking at the whole thing, I'm just going to focus on some manifold there. Okay. So I'm going to look at which submanifold. Well, knowing how I know that KdV is associated to the Schwarzian, I would look at D, right? So I will focus on the third order ones and then say, if I consider only the third order invariants within this manifold, am I going to get a Poisson submanifold here, etc. Okay? So assume I have a Hamiltonian function that depends only on D. Then I take K0. Remember that K0 was all the higher order stuff? I'm going to make it vanish, all the higher order ones, and then see what happens to these Hamiltonian evolutions. And lo and behold, what happens to evolutions when K0 goes to 0? If I have an evolution with a function that depends only on D. Well, the evolution blows up. Big deal. Okay, so when I saw this, I was really disappointed because I said, how can it be? What does this mean? That I have the wrong K0. Because it just blows up. In fact, it's the diagonals. When the diagonals vanish, the evolution blows up. Okay, so for the longest time, I didn't know what to do about this, because I couldn't think of any way to get rid of those diagonals. And the reason was because when you do this for the Lagrangian case, you take this limit, and it all works beautifully, right? It all goes, this is a Poisson manifold, it's all beautiful. So I didn't expect that this was going to blow up at all. And I was completely confused about it. Then I was working with Mike in a case that was relating the two Grassmannians in R4 to the conformal sphere. And then I realized, working on that case is when I realized that this case had more to do with the conformal case. That's two more conformal. I don't know if you have noticed. That, more to do with that, because I have the third for the end, more to do with that with the Lagrangian case. And the reason is the following. The conformal case needs what is the equivalent of a natural frame in Euclidean. And the natural frames are not local. They are solutions of differential equations. They don't depend on the jet. They are not local frames. So I had that, when I realized that, then I just went and looked for non-local frames for the spinor case, and then I got the theorem that says that there is an invariant gauge matrix that takes k to k hat. This is a non-local matrix, so you have to actually check that those form a basis for the differential invariance, the entries. But then k hat looks like this, and this is what the gauge does. These and these are the same. It doesn't change it. Now this changes, and now it's still a symplectic matrix, but the diagonals are 0. And what the gauge did was move this diagonal to the normalized entries. So now the diagonals are 0, and every other entry is an independent invariant of 4th and 5th order. Okay, so the problem was in the diagonals when I took. So once I did that, then you could prove that the level set is a Poisson submanifold, and that we're restricted to this. The geometric Poisson bracket that I had, the original geometric spinor one, decouples into families of KdV Hamiltonian structures. So KdV has two Hamiltonian structures that are well known, and suddenly you have this decoupled system of Hamiltonian structures when I restricted this manifold. So it was all beautiful. And then you look at the second one, which was the interesting. And then the second one, although it did not reduce to k, it does to this submanifold. So you can reduce the second one to the submanifold of Schwarzian type of invariants, and you get a decoupled system of the second KdV. Now you have a family of two compatible ones you can integrate, and it's all good because you just get, hopefully, a decoupled system of KdV. And this is guaranteed. Once you have this reduction, it's guaranteed you will get a geometric realization, which is given by the Spinor-Schwarzian KdV equation that looks like that. So if I start with equations that look like this, and I start with a flow of curves for which these higher order invariants are 0, then this evolution is going to preserve that level. The entire flow will have that property, and the invariance D, the block metrics, would satisfy a decoupled system of KdV. So you get these nice flows on spinors, and you get it also in Lagrangian, and you get it in the conformal sphere. You get it in all these parabolic manifolds, except for the one I don't know are the E6 and E7. I still don't know how to do that. Anyway, so where is the projective geometry here? Right? Where is the projective geometry that is generating all this KdV? Because my gut always told me projective geometry is the one that generates KdV. But these are spinors. This is a different geometry, right? Yeah, I forgot to say that you can get KdV, but you get all of the other ones that you can do in RP1. So you get a whole array of decoupled systems. Okay. So a projective structure on these curves as K0 go to 0. So you look at the Serefrene metrics when K0 goes to 0, and it looks like that. And as you play a little bit, you realize that this operator is actually equivalent to a decoupled system of second-order Hills equations operators. And this, so it's this one, or this diagonal. And these actually, each one of them define a projective structure on the curve. Because Hills operator, the solutions define a map locally to RP1. And that's something that one can check. If you take the homogeneous, this is actually, if you solve this for two solutions that are independent, you take the quotient, then that Ki will be the Schwarzschild of that. Actually, not the Schwarzschild, but twice the Schwarzschild. So you are defining a map to RP1. So this operator is defining n projective structures on these curves. So there is the question of what are these curves, right? And this is something I don't know, and I would like to know. So the only thing I know is that in the conformal last case, that's the last time I'm going to say, in the conformal case, the Fialkov, who was the one that classified the invariance for conformal curves, proved that the curves for which higher order invariance vanish are orbits of inversions. So you have these orbits of inversion elements, and those would be the curves that evolve by KdV, if I take them as initial conditions. In these cases, I don't know what they would be, and I would like to know what curves those are.
What about the case where it's not 2n, 2n, but 2n plus 1?
I have a hard time with that one because I can't find the K. I can't find invariance. It's a really complicated case. So I don't know that anybody knows what the invariants are for those curves, for the odd case. So I guess I should have said that's missing still, together with the exceptional. Does the G2 case? It's not. Yeah, it's a one gradations.
Okay.
That's another question. What happens if the gradation is higher and it's longer? And my gut is that it actually doesn't happen there, but I don't know. I don't know. Now, do you want to see the movie?
Oh, yes.
Hey. I was waiting for someone to say, well, what about the other movie? Yeah. Well, I left. He's not a fractal now. Okay, so I'm going to show you a movie of the real experts on producing vortexes. And it's not smoke. It's these guys. And this is just for fun. Oh, no, 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 wait, wait, wait. No, 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 you're not going. Yeah. You just have to wait to see what the guys do.
How they play with them?
Oh, yeah. But you can see how stable these things are. Yummy. It tries to rotate it. It's really nice. Anyway, that's the one.
Oh, these are bubbles, they blow it out of
They bubble and they blow it out of the hole. Yeah. They blow it out of the
Does
hole.
a whale make it even bigger?
Huge vortex that comes to you.